had a few over email, but if we have any questions, let me see. This is what I do for my high school students, so if you don't like it, tell me. Show me a 5 if you got it down 100%. Show me a 1 if you don't know what I'm talking about, or somewhere between. Okay. All right, so we have questions. We just don't know what they are. Is that right? All right, let's do a basic problem that let's look at the worksheet. You guys pick up the handouts today?
Both of them or?
Yeah. We didn't get a chance to do all of these exercises last time. Well, let's do some of them. So on the worksheet from last time, on the back side on section 4, any preferences which ones you want to do? Because if you've already done it, I don't want to do it. I want to do one that's going to help you. Any preferences, or should I just do the first one? What's that?
B.
B. Okay. So it says polysilin is available as a solution containing 250 milligrams per 5 milliliters. So in other words, this is when you go to the pharmacy, this is how they give it to you, right? Then it says, how many milliliters would you administer to give a dose of 400 milligrams of this drug? This is a story problem, right? So what's the very first step in solving any story problems? Any problem, period.
Write what you know.
Okay, we can start there. Write what we know. What do we know? We know we have medication from the pharmacy, or available medication, 250 milligrams per 5 milliliters. And what's another way to write that?
250 over 5 ml.
Yep, good. What's another way to write that? 5 milliliters over 250 milligrams. You with me? It's a conversion factor. That's all it is. So depending on where we start, and remember last time I told you, you can start wherever you want. Start with the given information, right? So here we have that information. We also have the doctor ordered us to take, or the patient to take 400 milligrams of this drug. Okay, we have what we know. What's our next step?
What would be?
Well, what do we want to know? What are we looking for? And what are we looking for here?
Milliliters.
Milliliters. How many milliliters of this drug will we give them? Of what's available from the pharmacy, will we give them? Will we give them? Everybody understand where we're at on here on this worksheet? We good? Okay. So where do we start? It doesn't matter, and I know that doesn't help you sometimes. Here's the way I look at it. I'm going to go with what the doctor tells me. What if it's not a doctor problem? Okay. This is what I was given. If I choose to go with this one first, that's okay. But I use my thinker. What am I looking for? Milliliters. So which one of these am I going to use? The one with millimeters on top. I don't want per milliliter. I want how many milliliters. Does that make sense in everybody's mind? Okay. So I'm going to use this one if I use this one to begin with. But generally, I like to use that one because it doesn't look like a conversion problem. But does it matter the order you multiply things in? No, it doesn't. Doesn't matter at all. All right. So where do you want to start?
With the milligrams?
Okay, so you want to start with the way I would do it? Maybe we should start with the way that your brain works and says, start here. Anybody else? No? Okay. What? All right. So 400 milligrams. Do I want milligrams in my answer? No, so where do we put milligrams? On the bottom. Does everybody understand why that works? Please raise your hand if you do not understand why that works, and I will show you. Okay. We have 1/2 times 4/3. Can we do this?
It'd take a while.
Okay. But there's a simpler way to do this rather than getting a calculator and just plugging and chugging. Can we see that this 4 is the same as 2 times 2, right? Can we cancel one of those 2's out? And when I say cancel, what am I canceling it to? A 1. Because 2 divide 2 is just 1. And what's 1 times anything? Itself. We don't have to write it. That's why we say it cancels. It goes away. Well, it doesn't really go away. We just don't have to write it. You with me? So this is 2/3. Did that take a while? No. If we do, there's another way to do this. We can say 4 times 1 on the top is 4. 2 times 3 on the bottom is 6. And then we simplify. Right?
2/3.
Okay? We get the same thing. So if we can see that something cancels, let's do it. And that's what we're doing. We want milligrams to go here because we don't want it anymore. We want to cancel it. What's milligrams divided by milligrams?
No.
1. And we don't have to write it. Does that make sense to everybody? Okay? But now we got to convert from milligrams to what? Well, we use what our given information to help us. We use that. We're not going to use that again, so just get rid of it. Does any of these have milligrams in it? The answer is yes. Go ahead.
Yes.
No, I'm just teasing. So right here, we got 250 milligrams per 5 milliliters. Milligrams cancel out, and I'm left with milliliters. Is that what I'm looking for? That tells me I know it's right because I just used information I was given. Okay, now let's go back to this problem. I can multiply everything on top and get an answer, multiply everything on bottom, get an answer, and then divide the two, just like you shown in critical chemistry. Or the way I like to do it, and listen, just because I like it a certain way doesn't mean you have to do it that way. All right? Do it the way that clicks in your brain. If you learned clear from elementary school that this is the way you should do it, and you like it, do it. Okay? I just like to do things faster. But that doesn't matter. Do it the way that fits in your brain. Good? All right. So in my calculator, I'm just going to type in 400, multiply 5 because it's on the numerator, divide 250 because it's on the denominator, and then push my equal sign. One calculation. I don't have to find an answer, then divide and find another answer. The more buttons you push on your calculator, the more room for error. Are we good? And so we get something. 8 milliliters. that right? Yeah. Is my sig fig okay? How many sig figs should I end up with?
The two after the zero are.
Should I use this number for sig figs or this number for sig figs?
The,
Go ahead, Parker.
Would you use the 400 because the 5 over 250 is just the.
That's a conversion factor, and conversion factors have how many sig figs? Infinitely many. Okay, but in this case it wouldn't matter because there's one sig fig. How many sig figs does 400 have? Just one. Remember, those zeros are not significant because there's no decimal. You with me?
yeah.
Okay. Yeah, so our answer should have one sig fig. But yeah, we'd use the 400 to determine how many sig figs. Are we good? Any other questions? We could do more of these, or we can move on. Go ahead, yeah.
Maybe just one more.
One more? Yeah. Let's do one with more steps.
Does C have more steps?
No, but D does. Let's do, which one is this? Drug dosages. Let's do D. I didn't give you space or right answer for C, sorry. Okay, so let's do D. Okay, drug dosages are often given as a mass of drug per body mass. You understand that? So you take a certain amount of drug depending on how much you weigh. Okay. For instance, milligrams per kilogram or micrograms to kilogram. And that first sentence is just information. Just well, not information to help you solve the problem, but just general information. What is the daily dosage in milligrams per kilogram of body weight for a child weighing 23 kilograms who takes 2 quantity milligrams tablets of this drug? A lot of information in that one sentence. So what's our first step?
Write what we know.
What do we know? You're right, that is a good first step. What do we know?
The child is 23 kilograms.
Good. 23 kilograms of body mass. What else do we know? QTY. What's QTY stand for? Quantity.
Tablets.
2 50 milligram tablets of drug. So, how do we write that? If the kid takes two 50 milligram tablets, how many is he taking? Taking 100 milligrams, right? $100 milligrams of this drug. And is that all we know? Yeah? What are we looking for?
The daily dosage, so how many milligrams daily?
How many milligrams? And he takes 100 milligrams per day, right? Because if it's a daily dosage, we have to know per day. And just like in critical chemistry, it says, okay, what are we looking for? And what do we started with? That's what critical chemistry tells you to do. If you do that on every problem in your entire life, you will be able to solve it. It's a good problem-solving strategy. All right. So where do you want to start? Well, we have 2 bits of information. Which one do you want to start with? None of them, because it has to do with math. No one has a preference? Okay, let's start with 23 kilograms. Sure. Or we can start with what the doctor told him to have, right? Doesn't matter. Well, let's do it. Let's start with 23 kilograms. Let's use dimensional analysis. Do we want kilograms in our answer?
Yes. We want milligrams per kilogram.
Do we want milligrams per kilogram for our answer? We have to know this. Read the question. What do we want to know for our answer? It says, what is the daily dosage in milligrams per kilogram of body weight? Oh, I didn't write that down all the way, did I? It's a good thing someone read it. We want milligrams per kilogram. That's what we want. See, if I would have just stuck with that, I would have got it wrong. I'm looking for the wrong thing. Okay, good. So now we do know what we're looking for. Milligram per kilogram. So what does that tell us? Should we start with 23 kilograms?
Or should we start with 23 kilograms per 100 milligram?
Ooh, can we start with 23 kilograms per 100 milligrams? Is that information given to us? Is it?
Yeah.
Where?
2 quantity 50 milligram tablets, that equals 100 milligrams per day.
So you said 23 kilograms per 100 milligrams?
Yeah.
Okay. It doesn't say that exactly, does it?
No, it says 2 quantity 50 milligrams.
But what it does say, it says a dosage is milligrams per kilogram or micrograms to kilogram, right? Or something like that. We are looking for milligrams to kilograms. Should we just do what it says? Milligrams divide kilograms? How many milligrams do we have? He's taking 100 milligrams, and he has 23 kilograms.
I mean,
Is that what I'm looking for?
It doesn't cancel, but it makes sense.
It doesn't cancel. But that's what I'm looking for. I'm done.
Oh.
Well, that wasn't hard at all, was it?
No,
Could we use dimensional analysis, guys? Could we use it?
We could, but didn't
Yeah.
they want it per kilogram?
There it is. Milligrams per kilogram.
Oh, I
Yeah,
thought
we're
it meant,
done.
like how many milligrams per 1 kilogram, but that would have been wrong.
It is. If we divide them, it will be per 1 kilogram.
Huh.
So what's 100 divide 23? 4.35
Yeah, about.
milligrams per kilogram. There we go. Now, if I started with the 100 milligrams, why would I start here? Because that's on top, and I want that on top. So this one almost wasn't dimensional analysis, was it? It was, because they tell us what we're looking for. We have milligrams, and we have kilograms. That's all we do. Are we good? And that is what dimensional analysis is. Using the dimensions, using the units to guide our thinking on what to do. Parker.
So what one would like determine how many significant figures then?
Oh, good. 23 kilograms. Is that a measurement?
Mm-hmm.
Yeah? So there's 2 sig figs. Is this a measurement? or is it a conversion factor? One tablet equals 50 milligrams.
That's a conversion.
That's a conversion factor. I would just go with 2 sig figs. So 4.4 milligrams per kilogram. Make sense? And let me tell you here, that is not the most important part, is sig figs. It's not. It's important, you need to know it, but it's not the most important factor, okay? So on the test I give you, it's multiple choice. So you don't have to type in the exact number like you do in critical chemistry, right?
Mm-hmm.
So you'll see which one it is, which one is closest to it, right? But there are some that you will have to use sig figs. There'll be specific problems on counting sig figs for the first test. Good? Any other questions? All right, are we ready to move on, or what we feeling?
Moving on.
All right. Okay. Okay, the atom. Raise your hand if you know what an atom is. Raise your hand if you don't know what an atom is. Okay, so some of us are just shy. That's fine. Okay. Well, the reason I ask you questions like this is so that I can know if I should really dive deep inside of it or if I should just skim the surface. And if you don't tell me, it's like, I'll either be wasting people's time because I'm telling you all this stuff you already know, or else I'll be leaving people behind saying, oh, what are you doing? So when I ask you questions, that's why. And again, who are we here for?
Ourselves.
We're here for you. Don't worry about what anybody else thinks, not even me. We're here for you. Good? All right. So, before we get in and talk about the atom, what it's made of, but everything that we see, everything we feel, touch, taste, is made of atoms, right? So let's talk about the atomic theory. Theory. What do you guys think? Uh-oh. I'm not talking to you, Siri. I know you're Siri. Get out of here. Okay, sorry about that. What do you think of when you hear the word theory? Go ahead.
Our best guess, but can't be proven.
Our best guess that can't be proven. Okay. Anybody else? Any specific theory come to mind?
Dalton's theory.
Dalton's theory of evolution? No. Darwin. I was thinking Darwin.
Who's Dalton?
We'll get to him. Okay. Sorry, I was thinking you said Darwin because that's what I was expecting. All right. Theory of evolution, right? We'll get to his theory. What about the Big Bang theory? Those are theories that people will either say, yes, that's the way it is, or no, that's the way it's not. There's a lot of controversy with those two theories. So, can we trust a theory? Charlie's saying no, we can't. What do you think, Parker?
Well, a theory's tested a lot. So.
Theories are tested. We don't just say, yeah, I think it's just like this because.
That's a hypothesis.
Yeah, theory is not a hypothesis. So a theory is something that is well tested, and as far as we are in knowledge or technology, this is what we know to be the case. But still, we have the theory of evolution and we have the Big Bang theory that people can't say yay or nay. It's either here or here. It's not like, maybe.
Nobody was there, so nobody knows for certain.
That's right. But do we have things that say, for example, the Big Bang theory? Do we have things that say that's what it comes from? We all came from a Big Bang?
Evidence.
Okay, yeah, we do have evidences. Are there holes in it? Okay, yeah. So, most theories are really close to laws. What's the difference between a theory and a law? Any ideas?
It's
Go ahead, Eric.
Like a lot of like some kind of like it's like true. It's like kind of like fact. Like it's not like cause like a theory like it like shows it explains that something
Uh-huh.
this way, but if like something small disproves it, then the whole thing falls apart. But like the law, but like the law of something like absolute.
Okay.
like
Yeah, it's hard to tell. It's hard to tell the difference. A theory, yeah, like Eric said, if we prove to be false, then we say it's something else, right? We go, oh, this tells us it's not this, so we redo it and retest, and okay, it must be this then, right? We make progress. We evolve. But what about a law? Can we disprove a law? Why not?
because otherwise it wouldn't be a law.
Who wrote the law? Who wrote it?
Some guy?
Some guy or some gal, right? Go
I
ahead.
think the law has been like agreed by most of the scientists, so it's already like set up as a law. And theory, most scientists didn't agree with it, so that's why it's still.
Good guess. And so, yeah, if we disprove a law, and yes, that is possible. If we disprove a law, it is no longer a law. If we disprove a theory, that's no longer our theory. They're almost the same things. Who can tell me what an atom is made of?
Subatomic particles that make up
Which are?
Protons, neutrons, and electrons.
Who agrees with that?
Oh, and something else that binds them together.
Okay, so we have hands that go up. You agree with that? How do we know? Because your 8th grade teacher taught you? Or your 7th or whoever, okay? Can we see electrons, protons, and neutrons?
We know they exist because it's possible to add and remove electrons from different elements.
But can we see them? They're too small. We can't even see atoms, ladies and gentlemen. They're too small. So you see why we call this a theory?
Because it can't be proven.
Neither can a law. But we don't have the technology to know for sure. Okay? All right, we're going to talk a little bit about this atomic theory. So way back in the BC times, this Democritus philosopher from Greek, he says this is what an atom is. Smallest particle, you can't destroy it, just small and invisible particle. And that's what everything's made of. Good? And then Aristotle, you probably all heard of Aristotle before, right? Well, he says there are 4 elements, right? Four elements. What are they? Anybody Avatar fans? Those are the 4 elements. What are they?
Hot,
Air,
cold, wind, and water.
air, earth, fire, and water, right?
They all lived in peace until the Fire Nation attacked.
But that's just Aristotle stuff. Are those only 4 elements, guys? No, we're going to talk about 118 of them. Well, not quite, but. So those are philosophers. They just think of stuff and say this is the way it is. And if they're tied into the church, then people say, okay, that must be true. And don't go against it, because otherwise you'll be a heretic and burn at the stake, right? And that's what they did with Galileo. He didn't burn him, but they put him under house arrest. And in 1993, they finally forgave him. Okay. Weird, right? So Aristotle was a smart dude. But then we move on to today's age. Not today, but probably in the 1400s, 15. I don't remember exactly. John Dalton, maybe 1600s, maybe 1800s. I don't know. I don't expect you to memorize that. But John Dalton, he come up with his theory, and this is what I want you to know. Write this down. So all matter is composed of atoms. So what's an atom? Can anybody tell me what the definition of an atom is?
Like anything that can occupy space and has mass.
That's matter. Good. So an atom is the smallest particle, I'm going to call it representative particles, of an element. You guys know what an element is? It's not air, water, fire, and earth. Did you guys get a periodic table over here? Those are all the elements, right?
Like plutonium, neon.
That's right. Okay? So an atom is the smallest particle, smallest representative particle of an element. That means the smallest particle of gold has the color of gold, has the density of gold, has the hardness of gold, has the shininess of gold. You with me? Okay, the next part of Dalton's theory atoms of a given element are different than atoms of a different element. So in other words, gold is different than copper. Gold atom is different than a copper atom. Do they have some similarities? Yeah. But they're different. We good so far? Am I going too fast? Do I need to slow down? Okay, next part is compounds. Compounds are simple whole number ratios of atoms from two or more elements. Can anybody tell me an example of a compound? Hydrogen chloride, HCl. One that we use every day. H2O. Good. So there's two hydrogen atoms for every one oxygen atom. Why isn't there a 1? It's like writing 1x. Do we need to write that 1? No, we don't. So there's 1 hydrogen to 1 chlorine, 2 hydrogens to 1 oxygen. We write the number after the letter. Are we good? You'll need to know that for the rest of this class. In fact, everything so far you need to know for the rest of this class. And the last part of this theory, atoms cannot be created or destroyed.
But isn't how hydrogen bonds work splitting an atom?
Nope.
Really?
Right. Can you split an atom? Yes, that's what an atomic bomb is. But can you destroy an atom? You cannot. Well, as far as we know. Right? That means atoms are ageless. And we're made of them. That means we're ageless. Okay, we good? Any questions so far? All right, this is the base of the atomic theory. We're going to build off of that. But we said an atom is made of protons, neutrons, and electrons, right? Well, this physicist named J.J. Thomson, he discovered the electron. Well, he didn't call it the electron first thing. It was later called the electron because of its electrical properties. How did he do it? He got a cathode ray tube. You guys know what cathode ray tubes are? You ever seen one of those big, huge TVs that are like big boxes?
Oh, tube TVs.
You ever seen one of those? Anybody still have one of those?
My grandparents.
Okay. No, those are basically cathode ray tubes. But it looks something like this. The ones that he used look something like this. Had gas in there, gas of, let's say, argon gas or helium gas or any type of gas. And then he hooked electricity to it. So positive end, negative end. And he saw a glow. This is kind of how the old TVs work, right? But he's a physicist, so he's playing with different charges, different magnets and charges, right? This is just what he's doing. He's playing with charges and magnets. And he brought a magnet around here. And this beam was deflected or repelled. What happens when you bring something positive to something negative? Anybody know? It's attracted. Do we all know that? What happens if you bring something positive to something positive? It repels, right? Well, magnets do the same thing with electricity. And he knew this, but it wasn't until he started playing with the cathode ray tubes he found, that means if I put the north end pole to it, it'll deflect it. Put the south end pole to it, it'll attract it. And that helped him to realize the things in here, the gases in here, these are negatively charged. So an atom is not just a small ball. It's a small ball with a bunch of negatives in it. Okay? We take something that we know about physics, and this is our best explanation of it. Good? And that stuck for a while. And then Ernest Rutherford, this time he was a chemist, right? So Ernest Rutherford, he wanted to see a little bit more. Okay, now we know that there's something in these atoms, and it's not just a big blob of mass. He did a gold foil experiment. Why gold? We use gold for jewelry too. Why do we use gold for jewelry? More than just because it's pretty.
Non-conductive.
Oh, it's conductive.
Oh, it
It's
is?
very good conductor.
Doesn't react.
It doesn't react very well. So it doesn't rust, it doesn't oxidize, it just stays beautiful, right? So that's why he used gold foil. Why did he use foil? Thin as he can get it, right? So we have this gold foil, even though I drew it blue. And then he got this particle shooter, and it shot alpha particles. And alpha particles, he knew at the time, was a positively charged particle. So he shoots it out here, and then he put this film around it. Because alpha particles are a little bit radioactive, okay? And we'll talk about that a little bit later today. And so he shot this in there, and most of them went through. None of them went straight through, and some of them came back. Since most of them goes through, what does that tell them? An atom is mostly empty space. Mostly empty space. Because these particles, they're relatively large. It's actually made of 2 protons and 2 neutrons. He didn't know at the time. Okay? But since some of them came back, it must have a positively charged center, or nucleus. Again, we're taking physics, the properties we know of physics that are true, and we build our understanding on what an atom is. So his theory turned into this. You ever see that model before? That was his model. We got the electrons from that guy. Mostly empty space. In fact, if we take a basketball, let's say the nucleus of this atom was the size of a basketball, the closest electron would be somewhere close to the airport-ish. Not exactly, but a lot of space. Okay? And we're not going to talk about how we might know that, but okay. And then we had other scientists that found other things we're going to keep it simple. That's all we're going to talk about, the theory. Now we're going to get into the subatomic particles, protons, neutrons, electrons. And you need to know everything about these. Any questions so far? All right.
Do you know what they called electrons before they changed it to electrons, or no?
A negatively charged particle.
Oh, okay.
Yep. That stands for relative mass. Relative charge. Location. And attributes. Okay, the first one let's talk about is a proton. Proton is just a lowercase p with a plus charge as the superscript. So instead of writing proton every time, I'll just say p plus, right? The relative mass, what does relative mean? Is this building large?
Relative.
Relative to my house, it's large. Relative to buildings at the University of Utah, it might be small. Or relative, right? Okay, you understand relative? So if we say the mass of a proton, well, the mass of a proton is something times 10 to the negative 24 kilograms. Tiny, 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 right? Almost zero. So that's why we use relative mass, and we actually use relative mass to figure stuff out, okay? Let's just call it 1. Why do we call it 1? Because it's easy. Are we good? And I'm going to teach you how to read the periodic table, and we use this 1 value, okay? Relative charge is plus 1. Well, the charge isn't really plus 1. It's 1.609 times 10 to the negative 19 coulombs. But that's yucky, right? Let's keep it simple. The location, anybody know where it's located? This is what makes it positively charged.
The center?
The nucleus, that's right. And the attributes of the proton determines the element. So this is the atomic number. If you look at your periodic table, the element number, that's the atomic number. What's the atomic number for oxygen?
8.
8. That means it has how many protons?
8.
8. Are we good? Okay, the next one are neutrons. What's the symbol for a neutron? And with what charge? Why do we call them neutrons? Because they're neutral. 0 charge. If the mass of a proton is a 1, the mass of a neutron is also 1. The charge is 0. Location is
Nucleus?
also the nucleus. Well, why? If protons are there, if you have more than one proton, like all atoms except for hydrogen has more than one proton, they're both positive, what happens? They repel, but they don't. That's because something is holding them together. What is it? Neutrons. Neutrons are nuclear glue. Okay? We'll talk about that a little later today. And the neutrons determine the mass number, or the isotope. We'll talk about these. Okay. Okay, and the electron is E minus. Relative mass is basically 0. We don't count it. If you really want to know, it's 1 over 1840, but we don't use that. We just say it's 0. Okay? We don't count it, ever. Well, physicists might count it, but in chemistry, we don't. Relative charge is -1. It's the same charge as a proton, same, it's 1.609 times 10 to the negative 19 coulombs, but it's negative. But we'll just say it's -1. Keep it simple. And where's it located? Outside nucleus. That's why J.J. Thomson found that there's negatively charged particles, because they're on the outside. And the electrons determine the charge of the atom. It also determines the properties. Let's talk about these. Why does the electron determine the charge and not the proton? Yeah, go ahead.
Because it would be a different element.
It would be a different element, that's right. If we ripped off an electron, it's the same element. How do we rip off electrons? We get a balloon and do this on our hair, and we stick to the wall. We just took some electrons off our hair and stuck them on the balloon, right? It's still hair. Didn't change what it was, okay? And properties. Why do electrons determine the properties, not protons and neutrons?
Because like it determines what it can bind to, like what it
But why?
because
Where are they located?
To make stable.
Because they're on the outside. When you touch your water bottle, what part of it do you touch?
The outside?
The outside. When you handle anything, you touch the outsides of it. What part of the atom mixes with the other part of a different atom? The outsides, the electrons. Are you with me? Okay. All right, so know this table inside and out. Good? Okay, I need to take a little break. If you guys need to take a break, let's do that. Or study that chart, whatever you want to do. Any questions so far? All right, so how many protons does carbon have? Real loud. How many protons does hydrogen have? 1. How many protons does gold have? AU. 79. So, it's kind of hard to find some of these, huh? So what should you do?
Highlight them in different colors by what they are.
If you want to, study them. Get to know them. I'm not going to give you a test on what the elements are, because you get to use this on any test, midterm, final. I'll give you a blank one of these, okay? But become familiar with them. Know where they are on the periodic table so you don't have to search to find it. Wasting time on your test, and then you get anxieties because, I can't find it, right? So, to help yourself, learn the periodic table. Learn the elements. Okay, let's talk about neutrons. First of all, it determines the isotope, right? Anybody know what an isotope is? Yeah, what is it? Eduardo?
Variation of like a different, it's the same element, but just like with a different different charge or different.
Yeah, different something. Good.
Yeah.
It's the same element. That means it has what? The same number of protons. It's an atom with the same number of protons, but different number of, not electrons, because electrons can change back and forth. Number of neutrons. That means the mass is different. Okay? What? Say that again. Chlorine? Not quite. We'll get there. I'll give you an example here. So, hydrogen has 3 isotopes, well, maybe more, but 3 main isotopes of hydrogen. Is hydrogen 1. In fact, before I do this, let me give you the symbol. So here's the isotope symbol. And I'm going to tell you right now, this is on the first exam. It's going to ask you, what is the A? The reason I'm telling you, because I think it's a stupid question. I don't want you to memorize what A is, but because it could be P or Q as far as I'm concerned, okay? But the number that goes in the place where A is here, this is the mass number. And what is the mass number? What has the mass of the atom? What consists? Neutrons and protons. Because electrons don't have mass, right? So it's going to be protons, the number of protons plus the number of neutrons. That's what the mass number is. Okay? This number down here is the atomic number. Atomic number is the number of protons, right? That tells you what element it is. And this C is the charge that's determined by the number of electrons, right? And we'll talk about how we do that, okay? So let's do an example of an isotope. We have hydrogen 1. How many protons does that isotope have?
1.
1, because it's hydrogen. How many neutrons does that isotope of hydrogen have?
0.
0. Its mass is 1. It has 1 proton. That means it must have 0 neutrons. You with me? How do you find number of neutrons? You subtract them. 1 subtract 1 is 0. 0 neutrons. Good? Okay, this is called protium. You don't have to know this. But that's one isotope of hydrogen. That's the majority of, that's like 99% of all hydrogen. Okay? Then you got another one that is hydrogen 2. This is called deuterium. And this can be found in the ocean. How many neutrons does deuterium have? 1. Has 1 proton, 1 neutron, both together make a mass of 2. You with me? And then you have the rarest of them all, and this is why Doc Ock had to steal it. You know what he stole? Tritium. He didn't really, guys. That's a fake show. Oh, I just bursted some of you guys' bubbles. I know. Okay. So this has how many neutrons? 2 neutrons, 1 proton. That makes 3. Good?
If it has 2 neutrons, there's a 1 in the neutron space.
There's no neutron spaces.
Oh, wait, never mind, sorry.
That's so the A, that's the mass number. That's protons plus neutrons. Z is the number of protons, and C is really protons plus electrons, kind of ish. We'll talk about that in a minute.
Sorry, I flipped it.
No, you're good. Well, that's a common misconception. People say, okay, the neutrons must be the top number. It's not. Okay, are we good? Let's do some examples. See if we can figure this out, because this will be on the test. Let's say we have plutonium 244. How many protons, neutrons, and electrons does this isotope have? Start with the protons. That's the easiest. How many protons does plutonium 244 have? Go ahead.
94.
How do you know it's 94? Because that's the number, the element number of plutonium on the periodic table. So you might have to look. Find it on the periodic table, and that tells us this is 94. Is everybody with me? Okay, so we got 94 protons. How many neutrons do we have? Tell me how to do it.
Subtract 94 from 244?
That's it. And we get something. 150? Okay, how many electrons do we have? What is the charge of this isotope? Any guesses? It's 0. It doesn't have a plus. It doesn't have a minus. That means it's neutral. Most elements, most atoms we talk about are neutral. But if there's no charge, it's neutral. So how many electrons does it have?
0.
Oh, it doesn't have 0. If it had 0, what would the charge of this isotope be? Positive 94. It has 94 because electrons are negative. So we have positive 94 for the protons, negative 94 for the electrons. That's a total charge of 0. So when the charge is 0, number of electrons is equal to the number of protons. You with me? Does that make sense to everybody? Question? Oh yeah, it's saying to make sense. Good. Good? All right. Let's do another one. Because these are so fun, right? You got to get these down. So keep doing them until you have it down. So let's do cesium plus Cesium-133. How many protons, neutrons, and electrons does this isotope have? Everybody, how many protons does it have?
55.
55. How many neutrons does it have? 78. And ladies and gents, don't get in the habit of just doing stuff in your head. I know sometimes it's easier because you don't have a calculator nearby. When you're on the final, when you're on the test or the midterm or the final, use a calculator every single time. Make sure you get it right, yeah? So we got 78 neutrons. How many electrons? Can anybody guess? When I say guess, I mean educated guess.
54.
54. What do you guys think? Does it have less electrons? Does it have more protons or more electrons?
More proton.
How do you know?
Positive.
Because it's positive, and protons are positive. How many more protons does it have?
1.
Just one more. And we know we have 55, so it must be 54. Are you okay with that method? I can show you another method. Who wants it? Okay, here we go. We have positive 55 because we have 55 protons. You with me? Plus, however many we have for our electrons, I don't know what it is yet, is equal to, what's that?
Invisible 1.
Positive 1. Let's subtract 55 to both sides. And the number of electrons is
Negative 55.
-54. Why does it say there's -54 of them? Because they have a negative charge. You with me? So if you're good with algebra, that's a great way to do it. If you hate it, you might want to try using it to get good at it, because algebra is useful. Are we good? Do we need another example? I can give you a million examples today if you want. No? One more? Okay, let's move on. Here's another example test question. That's E. Oh, by the way, I didn't tell you, what does the X represent? The element symbol. And if you look at the elements on the periodic table, the first letter is always, always, always capitalized. If there is a second letter, it's always, always, always lowercase. Write it that way. Okay? All right, so if we want to circle or pair up the isotopes. What's an isotope of this one here? A, B, C, D, E, or F? C. Why is it C? A and C are isotopes because same atomic number, same number of protons, and different number of neutrons. I circled the top number. Is that number neutrons? No. But if it has the same number of protons and they're different, that means they have different number of neutrons, right? Are you with me? Okay, what about B? What's an isotope of B? E. And then these two are isotopes, right?
D.
You with me? Questions on how to do that? That'll be a test question. Okay. Questions on anything so far? I've gone through a lot of the examples that you'll see on the worksheet. Are we okay saving that for the end and for homework if need be? Because the answers are also on Canvas, right? You guys all figure out how I put my stuff on Canvas in the modules? Okay.
Did we get through all of like the information stuff for the notes?
Today? No.
Oh.
No, I just, I normally go through the example problems on the worksheet,
Right.
but we're hurting for time. Because I took that day off and, all right. Ready to move on? Okay. This part right here is a little mathy, but it's not too bad. Do we all understand how to find the average? Anybody need a reminder on how to find the average? Okay, we'll get there. All right, so if we look at the periodic table, let's look at carbon. What's the atomic number for carbon? 6, and where does it put it? On the top? Yeah, so it puts it right here, and it has 12.01 or something on the bottom, right? So this right here is the atomic number of protons. And this right here is not the mass number, but the atomic mass. And what's the difference between the mass number and the atomic mass? Go ahead, Eduardo.
Is the atomic mass the average of all the isotopes?
That's right. It's the average of all the isotopes of that element. So if you take the mass of a single atom, it can't have a decimal number, right? It's protons plus neutrons, done. It's going to be a whole number. But if you look at the atomic masses on all elements, well, most of them, they're decimals, right? Because they're averages. So this is the weighted average, not just the average, but the weighted average of all isotopes of that element.
What's a weighted average?
I'm glad you asked. Your grade is based on a weighted average. What is your grade? What makes up your grade most? Most of your grade, sorry. Tests. Not a lot more, but it does. Like 20% of your grade is on tests, 20% of your grade is on critical chemistry, 25% is on midterms and finals, right? 10% on e-portfolio, and I think it's 15% on quizzes. I can't remember exactly, but something like that, right? So they're weighted differently. Same thing with the atomic mass. So let's do an example here. Let's do hydrogen 1, hydrogen 2, and hydrogen 3 for an example. Well, 97.5% of all hydrogen as we know it is protium, or hydrogen 1. 2.7% of all hydrogen is deuterium, and 0.5% of all hydrogen is tritium. Okay? Now, if I were to, let's say I have a bucket of hydrogen. I know this is not possible because the gas that comes out, right? I have a bucket of hydrogen. I grab inside that bucket and grab a handful of hydrogen. How much is hydrogen 1?
probably the majority.
97.5%. Exactly. Well, ish, right? What if Incredible Hulk grabbed a handful out of that same bucket? How much would be hydrogen 1? 97.5%. What if a 2-year-old grabbed a handful? How much of his hand or her hand would be hydrogen 1?
97.5.
97. So, does it matter how much I grab? What's an easy number of atoms that I should grab so that I can use it to help me find the average?
3. 1.
What is percent out of?
100.
100 per centum. Centum means 100, right? So it's out of 100. Whenever we deal with percentages, guys, 100. Let's use 100, okay? So if we have 100 of these, how many are hydrogen 1? 97.5. We can't really have a half, but can we just go with it for now? All right. So let's, before we get in here, I need to explain how to find the average. Let's say I got a 10% on my first test because I just didn't study or whatever. And then I said, okay, I got to really get in and try, and I got an 80% on the next test. And then it's like, oh, I need to work harder. I got to work harder. I got a 95% on the last test or whatever, okay? Can you guys take the average? How do we do it? We add them up and divide by
100.
however many there are. There's 3 of them, right? So it's 10 plus 80 is 90, plus 95 is 185. Divided by 3 is somebody?
61.
What is it?
61.66.
61.66?
Yeah, it's like
All right, yeah. Or by 7, okay. So dang, you should have tried harder, right? No, I was kidding. So that's average. That's regular average. You with me? Who's comfortable with regular average, finding the regular average? Okay, I can show you how to find the atomic mass just using the regular average. Here we go. And I will show you also how to do it the weighted average way. Okay? Okay, so what's the mass of hydrogen 1, guys? We're trying to find the atomic mass or the weighted average of the mass numbers. What's the mass of hydrogen 1? Exactly 1. Hydrogen 1 means it has 1 proton and 0 neutrons. You with me? And so its mass is 1. Relative mass anyway, that's what we use. So we have 1 plus 1 plus, plus 1 plus 1 plus, how many times are we going to add these 1s? 97.5 times, because we pulled 100 out of this bucket, right? You with me? What's an easier way to write 1 plus 1 plus 1 plus 1 97.5 times?
1 times 97.
Oh, yeah. That's why we do times tables, right? Okay. So that's just like adding 1 97.5 times, right? Plus. So the mass of this one is 2. 2 plus, how many times are we going to add it?
2.7.
2.7 times. You following me? And to save time, we're going to have 3 times 0.5 times. Are you with me? We just added how many numbers up?
Crazy.
Yeah, exactly how many? How many did we pull out of this bucket?
3.
100 of them. 97.5 of them are hydrogen 1. 2.7 of them are hydrogen 2, and 0.5 of them are hydrogen 3. You following me? So we're going to divide that by 100. Isn't that how you find the average? Okay. And here's how to find the weighted average, ladies and gentlemen. What's 97.5 divided by 100?
0.975.
It's 97.5% written as a decimal. Do we know how to do that? Plus, what's 2.7 divided by 100? 2.7% written as a decimal, right? Plus, that written as a decimal, 0.5 written as a decimal is?
0.005.
We just divided all of them by 100. So,
Now we add them up?
yeah, that's it. We can find it this way, or we can just find it this way. It's the same thing. Does that make sense in your head? Do we have any questions on that? Okay. So what's the average? What's the weighted average? Hopefully it's 1.008 because that's what it is on the periodic table, right? Is that what it is? I don't know. I don't know if I just plug these numbers out of my head. I'm not sure. Figure this out. Calculate it.
I did calculate it and it's 1.044.
Okay. So obviously these are not the right percentages, right? But okay. This is how you do it. And on the test, I'm also going to pick different random numbers. So you can't just look at the periodic table, oh, it's 1.008. You have to be able to calculate this. Do we have any questions? Yeah.
Why is there like a 2 and then like plus 2 and then plus 3?
Good. So it's the average mass number, right? The mass number here is 1, 2, and 3.
So if we have like an element with a higher mass, we do like
A bigger number, yep.
2.
Do you want to do another one?
Yeah.
Okay, let's do another one. And again, I'm just pulling numbers out of my head because I don't have these down. Okay? Let's do chlorine. There's chlorine 35 is most of it. Let's say is 77%. And chlorine 37 is, to keep it simple, is 23%, right? Are we good? Now, which way do you want to do it? The regular average or the weighted average way? The weighted average way might be simpler because you don't have to worry about dividing by. What do you want to do? What? The weighted, yep, sure can. So we're going to take the mass of chlorine 35, which is 35, and we're going to multiply it by the relative percentage, or take the percentage and turn it into a decimal, right? 0.77. And we're going to add that to the mass of the next one, which was 37, times by the relative abundance of that one, which is 0.23. And that's it.
Well, then you gotta add them.
Oh, yeah, then you got to add them. Or Eve, whatever you want. Sorry.
Whatever floats your boat.
So like for example, in like the last example, it was like 97.5. Were we doing like the average?
Yeah, so right here, I just did the average, right? Just the regular average.
And then for the other method,
This one right here. I just changed this to a decimal
Oh, so we.
by dividing by 100,
Okay.
right? Because I'm dividing by 100 anyway. So both of them, you're doing the exact same thing, just in different orders.
Okay, yeah, cause like, 'cause I'm just making sure, like, for the second method,
Uh-huh.
I can just like move the decimal like 2 places.
That's it.
Yeah.
And that's how you do it. Yeah, that's how you change a percentage into decimal, by just dividing by 100. Or move the decimal 2 places over to the left. Make sense? Good, thanks for asking. And so what do we get here? 35.46? Holy crap. That was pretty close, actually. If you look at the periodic table, what is it? 4.8? 4.5? Okay. Pretty close. Okay. And, I'm missing something with these numbers. What am I missing? I told you last time, don't leave a number naked. I didn't tell you that part, but go ahead. I need a unit. What is it? 35.46 what? What is this? This is the atomic mass, right?
Oh, grams.
Oh, grams? So the is it for one atom? 35.46 grams for one atom of chlorine? What do you think? That's a lot of grams for one atom. Can't be, right? Now, your book uses AMU. Anybody know what AMU stands for? Atomic mass unit. Does anybody know how long this table is? It's probably about 6 DUs. You guys know what DU is? What is it? Distance units. Is that stupid? Would that be stupid for me to say this is 6 DUs? Would anybody know what you're talking about? No, do you see how that's stupid? So are AMUs are stupid. Sorry, this is trying to get this off my chest. Okay. It seems like every textbook calls them AMUs. Why don't you just call it what it is? So I'm going to call it what it is. But why am I telling you AMUs? Because the book says it. And I think there might be something in your critical chemistry that uses it, and can't get away from it because everybody wants to use AMUs, right? But here we go. Breathe in. Okay, we're good. I'm just teasing mostly. Okay, instead of AMU, we're going to say grams per mole. We're not going to talk about what a mole is yet, and maybe that's why they do. It's because moles are a little bit later. But moles is the amount of matter. It's the SI unit for the amount of matter. Okay? So grams per mole. We'll talk about what a mole is later. But those are the units, and they're not written on your periodic table. But it says 12.01 for carbon. It's 12.01 grams per mole. If you have 1 mole of carbon, the mass of that 1 mole is 12.01 grams. You with me? So that's what AMU is. But we're going to use grams per mole in this class. And Are we good? Okay. Any questions on how to calculate the atomic mass? So you'll be given all that stuff, you just have to calculate it. Good? All right. Okay, well, we're cutting out of time here. We're almost there. All right. Give you a few more definitions. An ion. Does anybody know what an ion is? An ion is a charged atom. That's it. Okay? It's also a car these days, right? You guys ever see the commercials about, is it the Hyundai Ion? I don't remember. But, okay, why do they call it the Ion? Because it's an electric car, right? That's a good name for it. Ion is a charged atom, okay? And there's two types of ions. We have cations, which are positively charged ions. And anions are negatively charged ions. And next unit, we'll be talking a lot about these, okay? But for now, I'm just going to talk about how atoms become charged. One more definition, and that is valence electrons. Electrons are important because they're on the outside. They're the only part of the atom that changes in a chemical reaction. You understand? If the nucleus changed, we'd have a bomb going off, and that doesn't happen. Not just a regular bomb, an atomic bomb. That's bad news, right? Okay? So valence electrons, it's a special name for uh-oh. It always did this in my other classes, and it never done it in this class. I thought, oh, this class is better. Hold on. Valence electrons are electrons on outermost energy level. I say energy level because that's what it is, but it's just the outside of it, okay? All right. So let me show you how you can use your periodic table to tell how many valence electrons there are. Wouldn't that be nice? So you don't have to memorize this stuff, okay? It's right here. This group has one valence electron. The second group has two valence electrons. The 13th group has 3 valence electrons. The 14th group has 4. Then 5, then 6, 6, I'll just write it, 3, 4, 5, 6, 7, and 8. Notice how on this periodic table it says 1A, 2A, 3A, 4A, 5A, right? Okay? That's how we tell. These ones right here we'll talk about later. We can't tell on those ones by looking at the periodic table. We'll talk about those later, not even this unit. Okay? So this is the valence electrons. Okay? Now, there's a group of elements on the periodic table, and that's this group right here. These are called the noble gases. What does noble mean? The high and mighty, right? Does everybody want to be noble? Yeah, so do the elements. All the elements want to be noble as well. Why? Because these guys have a full set of electrons. They're completely full. Have you ever driven down a highway with a full tires? Hopefully all the time, right? You just go smooth, right? Ever have a flat tire? Fa-bum, 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 fa-bum. Drives you nuts, right? Oh, I got to change this tire. I got to fill it up or whatever. Okay? These guys are flowing, not thinking of the right word, smoothly, right? Because their valence shell, or their outermost energy level, is completely full. And all of the other electrons are not full. So they try to become like that. And we call this the octet rule. What does octet mean? What does oct mean? Octagon, octopus, 8, right? Well, these guys have 8. Well, except for helium only has 2. You need to know that exception. Helium only has 2 valence electrons, and we'll talk about it next time. More why it does. But the octet rule is atoms will gain or lose or share electrons to become like. They don't become noble gases. They become like noble gases. Meaning they're balanced. They go down the highway with full tires, right? Well, that's just an analogy, right? Are you okay with what the octet rule is? Okay. And so, group 1, these guys have 1 valence electron. How many do they need to have 8? 7 more, right? Or they can just lose that one, and then they'll have a full octet. Because, let's say, for example, sodium, if it has 9 protons and it's neutral and it has, 11 protons and it's neutral, it has 11 electrons, right? If it were to get rid of one, it now has 10, just like neon. Or it can gain 7 and have 18 like argon. What do you think is easier?
Lose the one?
Just to lose one, right? It's closer to that one. So whatever one it's closest to, that's the one it's going to try to behave like. So this is plus 1. Why plus 1? If it loses an electron, what's the charge of an electron? Negative. If it loses a negative, it becomes more positive. Do you get that? Group 2 is going to be positive 2. Group 3, 13, is going to be positive 3. Then let's go over to group 17 is going to be, what's it going to do? It has 9 and it wants to have 10, so what does it have to do? It has to gain an electron. Electrons are negative, it's gain a negative, so it's going to become negative 1. Group 16 is going to be negative 2. Group 15 is negative 3. And I'm not going to do that one because that one's going to share. And we'll talk about that next unit. You with me? Am I giving you too much information so far today? Or are we doing okay? Do you understand how to tell? Now, on your periodic table that I give you for the midterm, won't have these numbers. It'll have the group numbers. Can you figure out what the charge is of these ions? Let's see. Potassium. What's the charge of potassium going to be? If it turns into an ion? What? Positive 1. Because it has 19, and the nearest noble gas is 18. It's going to lose 1. What? If it loses 1 or get... It will lose 1. So if it started as neutral, right? So 0, and it loses is subtract or add. Subtract is lose, and we lose 1 electron. Electrons are -1, right? What's 0 minus a -1? +1, right? You with me? And you can type this in your calculator all day long, and it's going to give you positive. But if we have 0 and we add a -1, that's -1. Are you with me? So don't think, oh, it's just you do the opposite of what you think. We got to know what we're doing. We're adding or losing electrons which are negatively charged. Are we good? And here's what a student, I've been teaching this for 15 years, and a student this last school year, he says, well, there's an easier way to think about it. If anybody just wants to this isn't why, but this is a good way to think about it if you want. Anybody need something else? Here it is. You look at an element, 56. The nearest noble gas, the closest noble gas is 54. It's 2 more than it, so it's 2 plus. If you look at this one right here, that's 34. The nearest noble gas is 36. It's 2 less than it, so it's 2 minus. Make sense? But it only works for these guys right here, guys. We're not going to talk about how many valence electrons there are for the other ones. We will, but not by looking at the periodic table or knowing what the charge is. Good? Any questions? Oh. We only have 3 minutes left and we're not done. We might have to call it. Sorry. We'll finish this next time. Are there any questions on anything we covered so far today? I'm sorry we're pushing. We will get caught up by next time, hopefully. But listen, if we don't get caught up, in fact, I want to stress this because I looked at the grades. Does everybody listen? I looked at your grades, and I seen some of you took the quiz on Unit 1.2 already. I mean, you can do what you want, but we haven't learned about it yet. Oh, but it says it's due. No. Those due dates are not the due dates. Don't take a quiz until we learn the material. Okay? So we're a little behind. That means the due dates should also be behind, right? We're behind. Don't push to get everything done on the due date. You with me? Okay. Have a great rest of your evening and drive safe.